So in this final section, we want to touch upon the idea of the random forest, which is a really powerful algorithm that all machine learning students should understand well. But we need to recap. So far we have the concept of bagging. The idea of bagging is that we're going to resample T datasets. Each of these tilde D T datasets is going to be created through bootstrapping, where we're just sampling the original dataset with replacement to obtain new datasets where some of the instances are missing and some of the instances are duplicated. We're going to obtain a base classifier for each one of these datasets by running the individual machine learning model on this. And we're going to return an ensembled classifier by taking a uniform vote of how each of the individual classifiers classified the X example. And we saw that this helps to reduce variance by voting or averaging in the case where we have a regression variable. Earlier in the pre-lecture, we talked about decision trees. The decision tree algorithm recursively chooses attributes to decompose a larger learning problem into a collection of subproblems of smaller size. It does so by choosing a particular attribute to split on. We choose the attribute with the highest information gain and build a classifier for each of the separate subsets of examples that have that attribute set to a certain value. And we are going to return the hypothesis, which is basically using that hypothesis against each of these individual classes over all of the decision tree paths. This has great performance on the training data, but because it has large variance, it can have a big problem with overfitting if we don't prune it. So in the random forest, what we'd like to do is attempt to get the best of both worlds. Can we aggregate the aggregations? Sure, we can do random forests. We can use the decision tree learning algorithm and pair it with bagging. So the idea is very simple. We're going to sample each of the DT datasets as in bootstrapping and then create different decision trees on each one. And we're going to vote on each of them. And this will be very nice because it's very highly parallel because we can do each of the decision tree learning algorithms separately, and it's actually quite fast to learn because the decision tree learning algorithm uses the choose attribute function, which runs pretty fast if we have a small finite number of attributes or dimensions of our data set. It inherits the pros of decision tree learning algorithm, but because we're ensembling it into a forest, the threat of overfitting is ameliorated to an extent. However, it's important to understand that random forest is not just simply bagging with decision tree learning. Otherwise, it would just be called decision tree bags. There's another element that makes it very useful. The key secret ingredient in random forest is by doing diversity in another way, by feature projection. To understand this, let's think about bagging again. Bagging means that we sample examples from the original data set with replacement so that we can get data randomness. But we can try to get randomness from another source of diversity in terms of the features themselves. We can randomly sample some number of features from the input space and use only that subset to build a decision tree. Unlike bagging where we sample the entire set M, of course this is again arbitrary, we often use a smaller data set of M prime, which is much smaller than the original data set, so that we have a very diverse set of trees that are generated. We'll usually use a criteria something like taking the square root of the number of features as a way of computing the inputs for each of the individual trees in a random forest. each of the random forest trees resamples a new feature subset of square root of n for each individual tree. This builds the idea of a random subspace. We're not going to use all of the features, but just a certain set. We can also refer to that as feature bagging or attribute bagging, in contrast to the normal bagging algorithm, which is an instance-based bagging. So we need to explain why we use such a small sample of inputs, the square root of n, rather than a larger amount. You can see that sampling with replacement probably wouldn't work very well because having the same feature illustrated in multiple columns in the decision tree would not help. The problem with using a large fraction of the dataset is that the same salient high information gain features are likely to be the same over different samples. So if we want to guarantee that our decision tree learning algorithm actually generates fairly different and diverse trees, we have to use a much smaller subset of features. The result with using a smaller subset n prime, such as the square root of n, is we get a more diverse set of hypotheses. The idea of such random subspaces is applicable to other classifiers and not just decision trees, with the variant of random forests. So in summary today, we've seen decision trees in our pre-class lecture. While they're very expressive, they can overfit to achieve a training error of 0. And we need to use pruning to combat the variance problem that happens with a particular sampling of our input space as represented by our dataset. In the post-class lecture, we looked first at bootstrap and bagging, where we sample a new dataset with replacement from the original. And with each generated new dataset ~dt, we can train a new hypothesis and apply uniform voting to get the result. This helps to lower the variance problem through the averaging as applied through the uniform voting. So to improve upon this, we looked at boosting. The idea was to make a strong classifier better from using simple weak classifiers. The idea is that we reweight each of the datasets at each time interval by accounting for which examples we got right and which ones we got wrong. This lowers the bias because we can use simpler hypotheses to create the learning algorithm. And we can prove outside of the lecture that this gets an optimum classifier if we continue to use boosting in the limit. Finally, we looked at the idea of the random forest classifier that combines bagging with decision tree learning algorithm, which introduces the idea of feature projection as an additional form of diversity, which goes also by the name of feature subspaces or feature bagging. Each of the individual hypotheses is tuned to some subset of the features as well as certain elements in the dataset. The bottom line from all of this is ensembles are just like the ensembles that you hear in music, like orchestras, having a diverse set of instruments or hypotheses that are understanding a particular piece of music or dataset is helping us to have good performance or good sounding music.